It's great to be here and talk to you guys about the work we've done recently on these fraction quantum anomalous effect. So the effect I talked to you, right, is belong to the family of quantum Hall effect. And I think the discovery of quantum Hall effect actually is a story of the pursuit of technologies. So back to the 1948, we know these three gentlemen at the Bell Lab, right? They discover transistors, basically, these germaniums with point contacts. And these discovery, right, later awarded of a Nobel Prize in physics, but really, I think it's revolutionized these microelectronics, right? From everybody knows, right? From these vacuum tubes into the desktops, and then to these hardware electronics we have now. So the pursuit of these technology, right, about these how to make better transistors, still continuing. Right? Here's just a chat from these TSMC, right? They're making transistors smaller and smaller, all the way to 5 nanometer, and there's rumors about 1 nanometer transistors in the next couple of years. So during these pursuit of technologies, and comes with these I think one of the most beautiful discoveries in condensed matter physics, which is the quantum Hall effect. So the image I show you here, actually, it's a silicon field effect transistor was used to measure this quantum Hall effect. We know that when you have a 2D electron gas, right, in this transistor, for example, apply a magnetic field, right, perpendicular to this 2D electron gas, then when you measure these Hall resistance, okay, across a sample, you will see that the Hall resistance is quantized in particular values. And a simpler way to look at it is look at the Hall conductance. They are quantized in an integer value and in the units of E square of H. So this is known as a quantum Hall effect. So a couple years later, the sample quality is improved, means the disorder is lowered. In this case, now the electron-electron interaction effects become appreciable. Therefore, in addition to these integer quantum Hall effect, they also, right, for example, in the Hall resistance measurement, you see another plateau at the fractional filling of these Landau levels. In this case, it's 1/3 fillings. So you can think of in the quantization measurements, how conductance can be quantized in the fraction value in a unit of E squared of H. So this now we know as a fraction quantum Hall effect. So if we look at the sample, right, they used to measure these fraction quantum Hall effect, on the millimeter scales. I don't think the sample looks particularly impressive, right? You look at these contacts, I think compared to the state-of-the-art lithography technique, it's pretty lousy, I think. The sample is pretty large and it's kind of dirty. You see all these, I think it's a silver paint or something on top of the surface. But with these samples, you still see these beautiful quantizations. So it means this collective behavior of electrons is governed by something beautiful inside the samples, right? Give you these quantized values of Hall conductance. And we now know, right, this something is called topologies. So we know topology, right, is for physical system that defined by topological invariant, which is means it's a quantity, right? It doesn't change by local perturbations. So here, the example I give it to you is a golf ball and also a cup. Here, the topological invariant is a number of holes in the systems. So even golf ball and the cup have very different, physical functions, right? The shape are different, but in terms of topology, are the same because the number of holes in the system is 0. Means the golf ball you can think of, right? They can transition or transform into this cup without break it apart. And then we can also have a coffee mug and a donut. These two belong to have the same topological invariant. In this case, it's 1, right? Because we have 1 hole in the systems. Now you can also have a topological invariant with 2, with a pair of glass, and with 3, with the prisms. So what the scientists, what they found is that these topological invariant actually can use to describe these quantized Hall conductance, right, in these 2D electron gas systems. So at least what David Solis did. So this is really kind of a cartoon-ish picture, right? Show how these electron conductance is described by the topological invariant. But what David really did is with his collaborator, right? What they found is that the quantized Hall conductance can be described by this formula. Here, C is now it's a chain number, and determined by the integral of barrier curvature over the first Brownian zone on the momentum space, and normalized by these 2 pi. So this shows that the quantized Hall conductance indeed has this topological invariant, right? It's independent of systems. Okay. So in this derivation of this TK-Kn formula, they use magnetic block wave functions actually. So it's independent of Landau levels, and so it's already that's the origin of translators. And later on, they extend this theory into the system with many body interactions and also substrate disorders. Okay, then they found is that the fractionally quantized Hall effect also has this topological invariant, basically can describe the same chain number C. Now you have this fractionally quantized Hall effect. And in this derivation, actually they also use block wave functions and no magnetic field. Okay, so there's no Landau levels, no magnetic field. It should be considered as already the early version of these fractional topological insulators, or fractional chain insulator. But when I talked to Chen Yu, so they actually didn't realize the importance of these, without magnetic field, because the focus, right, at the 1984 is trying to explain the origin, the topological origin of these fractional quantum Hall effect. Okay, but they already show how you can calculate these many body chain numbers in the systems. So there's a lot of interesting physics associated with these fractional quantum Hall effect. One of the important concept is anyons, right? We know that the fractional quantum Hall states can be described by anyons, and some of them even non-abelians. In addition to of a fundamental interest, and these non-abelian anyons actually can use for fault-tolerant quantum computations, right? So we know that for these quantum computings, error correction is a big challenge. So what Kateev pointed out is that use these anyons, you can overcome this challenge and realize these fault-tolerant quantum computations. So there's many schemes has been proposed to realize these non-abelian anyons, right? Either use these fractional quantum Hall states, some of them can be non-abelian anyons, or you can construct the devices such as a interface between a superconductor and the fractionally quantized edge states. So in these type of structures, you can realize called parafermions, and the parafermions can also use for construct fault-tolerant quantum computations. So since the theory already laid out the groundwork, how you can use, construct non-abelian anyons and towards fault-tolerant quantum computations, why it hasn't happened yet? Well, the reason is that it's difficult, right? Because all the scheme is based on this fractional quantum Hall effect. And we know that the fractional quantum Hall effect is fragile, right? It requires really low temperatures and also needs a high magnetic field. So high magnetic field actually, right, it's an enemy of superconductors. So this basically kills all the proposals, how you can use a superconductor to interface with fractional quantized edge states. Then the solution will be a fraction quantum Hall effect, but at a higher temperature and without magnetic field. So the first concrete example of this quantum Hall effect without the Landau levels at the zero magnetic field is pointed out by Duncan Haldane, right, in his famous toy model, the Haldane model. So he proposed these honeycomb lattice structures, and inside this honeycomb lattice structure, right, there's a spatially periodic magnetic flux, but with total flux in the unit cell vanishing. So in this model, he pointed out that, right, this particular model, right, is unlikely to be directly physically realizable, okay, because it's hard. But it indeed, right, shows that, we can realize this quantum Hall effect, but without the external magnetic field, but it could occur as a consequence of a magnetic ordering in a quasi two-dimensional systems. So these spontaneous time reversal symmetry breaking, right, can be provided by these magnetism in the system. So Houden's model doesn't consider spin, so it's a spinless model. Then we know that back to early 2000, Charlie King and Eugene Milley, they add these spin optical coupling, right, into this honeycomb lattice, and we realize these quantum spin Hall effect in graphenes, and find out it's a Z2 topological orders. So this model actually pointing a way to realize this quantum anomalous Hall effect. Okay, like Duncan pointed out, is that this King-Milley model, right, can be considered as two copies of a Houden model. Right? One copy is we spin up, the other copy is we spin down. So if we can break the time reversal symmetry of this King-Milley model, then you can just leave one. You can break the degeneracy, right, with these two copies. Then you can get the Duncan Houden models. Okay. So at the 2013, right, the group in China, right, led by Qipeng Xie and his student Cui Zhuchang, they discovered this quantum anomalous Hall effect in magnetically doped topological insulators. Okay, so the essence is that if you measure these Hall resistance, right, you will see it's quantized at the zero magnetic field in a unit of the h of v squares. And at the same time, the Rxx is suppressed. So if you see a quantized Rxy and we suppress Rxx at the zero magnetic field, it's evidence of a quantum anomalous Hall effect. So this is really pretty, right? I think this is really a milestone work. Now the question we ask is, well, is there any fractional version of this quantum anomalous Hall effect? There's a long history of work actually describe, to study these fraction quantum Hall effect, but without Landau levels, basically in the lattice systems. So the early work is by Bob Laughlin, and he considered, for example, right, the fraction quantum Hall effect, but in a spin lattice. Okay, and also there's work from Nick Reid and discuss these fraction quantum Hall effect, but in periodical potentials. And then at the 2000, right, there's many works consider these fraction quantum Hall effect, but in the optical lattice systems, such as cold atoms. Okay, there's many of them. So all these works, they consider you can actually realize these fraction quantum Hall effect in the lattice systems, but still you need the magnetic field. So the zero magnetic field version of this fraction quantum Hall effect is firmly established at the 2011 by a number of works, right? All these works, have different flavors, but the take-home message is that to realize this fraction quantum Hall effect at the zero magnetic field, you need a flat chain band. Okay, so chain band means the band itself has to be topological, and a flat, right, will give you strong interactions and a possibility to, right, give rise to these spontaneous time reversal symmetry breakings. So now the question becomes, how can we realize the system with flat chain band? So there's many theoretical proposals and efforts being into this field to kind of realize, to find a physical system with flat chain band and to study these zero magnetic field, right, fraction quantum effect. But we know that it's really challenging. So one of the problems in material system is Moiré superlattice. And I think many of you probably know, right? So basically, if you have two sheets of 2D materials, if you stack on top of each other, if they either lattice mismatched or matched, but with a little twist angle, you have these superlattice structures, right? Called Moiré superlattice, because of the interference of these crystals. So the power of these Moiré superlattice is already, shown by 2013, for example, right? The work done by several groups is that when you interface a graphene with a hexagonal boron nitride, and you form these Moiré superlattice, And in such a system, right, this fractal quantum Hall effect actually being realized. Then Alan McDonough also pointed out is that if you stack two sheets of graphene together, and there's a match angles. So in this match angle graphene, there's a flat band and with very large density of states. And this proposal being realized by Pavlov's group at MIT, they show that in these match angle graphenes, there's unconventional superconductivities and the strong correlated physics effect. So this really pointing out that direction how to engineer these strong correlated systems using Moiré superlattice. So there's already a few proposals to use these match angle graphene to engineer chain insulator and also fractional chain insulators, right? And we know that these quantized Hall effect indeed realize the match angle graphenes and also in TMDs. There's also progress towards these fractional chain insulator in these graphene systems. The example here is that in a superlattice formed by bilayer graphene with hexagonal boron nitride, if you apply magnetic field above 30 Tesla, right? So there's states as the fractional chain insulator states appears, right above these 30 Tesla. So these measurements is capacitance measurements. Basically, you measure the thermodynamic evidence of these fractional chain insulator. And there's another work from the collaboration with Pablo and Amir Yacobi, right? What they did is use bilayer graphenes, right, at a near magic angle and aligned with boron nitride. They also observe these fractional chain insulator states, but now the magnetic field is lower, right, at the 5 Teslas. So in both cases, right, they all need the magnetic fields. And now we come back to these questions, right? How can we realize these, zero magnetic field fractional chain insulator? Right? The observable is that there will be a fractional quantum anomalous Hall effect. We should observe these fractional quantized anomalous Hall effect. So that's gonna talk to you today, right? We realize these fractional quantum anomalous Hall effect, or FQAH, in twisted MoTe2 bilayers. So in the system, we have these few states, right? We have these quantum anomalous Hall state with chain number -1, and also we have these fractional chain insulator states at these 3 fractional fillings. So here the 3 works we have, towards these directions. The first one is we identify there's a ferromagnetism in the systems. So that's important because we know that we need a spontaneous temporal symmetry breakings, right? Then we show that how we can use optical technique, right, to measure these topological states, basically as these strata formula analysis, like thermodynamic evidence. Then later on, we also perform transport measurements. So that's what I'm going to talk to you mainly based on these works. So the system I talked to you is quite robust, right? Now we know that there's several groups also able to measure these fractional quantum anomalous Hall effect, either in these optical sensing technique or in the transport measurements. What's really exciting is that even beyond the twisted MoTe2 I talked to you, right, there are also observation of these FQAH in pentalayer graphene in the Moiré superlattice systems. So now we already have a 2 material system to observe these FQAH. Okay, now I'm going to talk about these material systems, right? We use these monolayer transition metal dicotonates, and they have these honeycomb lattice structure, and each corner, right? One is metal, the other is cocktail. So the inversion symmetry breaks. So these inversion symmetry breaking actually give rise to these valley constructing physics. So the means is that we have a valley dependent barrier curvature and also magnetic moment. So these valley dependent physical property is important for engineering topology of the systems. And when you stack 2 sheets of MoTe2 on top of each other in this rhombohedral stacking and with a little twist, they form these synthetic honeycomb lattice structures. So there's 2 sublattices in the system we call B and C. So these 2 sublattices, B is with metal on top of cocktail we call MX, right? So you can think of a pseudo spin pointing up. Then you have another sublattice C, which is XM, which is a cocktail on top of metal. Now you can think of a pseudo spin pointing down. So these two sublattices, they are energy degenerate. So they form these honeycomb lattice. Okay, so it's important. We have honeycomb lattice now in this from heterostacking. And has been pointed out by Allen and McDonough and his collaborator, right? In these honeycomb lattice, right? In synthetic honeycomb lattice, especially in twisted MoTe2, the top of valence band is topological. Okay, so that's very important. Then he shows that it's basically a system, right, to realize these King-Millet models, and there's a rich set of broken symmetry in state, right, at the integer number of electrons per more unit cells. So that's very important. Basically shows that in this system, twisted MoTe2 is topological. You have a flat chain band. And later on, my friend, collaborator Wang Yao, and his collaborator also point out that in this system, because of they have a real space Barry curvature effect, and they give rise to these pseudo magnetic field effect and also topology of the systems. And using these twisted TMD system, right? First of all, the group of Kai Chun and his collaborator Zheng Lin, they show that there's a fractional translator actually in twisted MoTe2, and also the work from Liang Fu, the Valentine and their collaborators, right, shows that in twisted WSE2, you can also engineer fractional translators. So all these work actually motivate our experimental progress. So let me just briefly mention, right, the topology, where the topology coming from the systems. So if we look at the electrons equations of motions, right, two of them. One is to the the position of the vector of the electrons. The other is the crystal momentums. So important is on the right hand side, right, for these velocity term, we have these k dot cross omega k. So omega k here is the curvature in the momentum space. So that's the pseudo magnetic field we know, right, in the momentum space. But the second term, which usually we ignore, which is r dot cross omega r. So r dot is just velocity. Omega r is the Barry curvature in the real space. So usually give you a crystalline lattice because it's a homogeneous crystals. So these Barry curvature in the real space actually vanishes. Okay. So we don't consider the second term here. But however, in the Moiré superlattice, right, it's not a homogeneous crystals. As I already pointed to you, for example, we have two sublattice B and C. B is metal on top of cocktail, right? It's a superlattice pointing up. C is cocktail on top of metal. You can consider superlattice pointing down. So now if you electron, right, you're saying I'm gonna move this sublattice B to C with pseudo spin pointing up all the way to pseudo spin pointing down. Then this pseudo spin will be rotating, right, in a real space, or rotating like this. So when it rotates in a two-dimensional space, then they form these layer pseudo spin skirmions. And we know that if you have a skirmions, then you will have a real space Barry curvature and also has emergent magnetic field. So that's gives rise to these topological phenomena in these homobilayer system. Okay. So the first, what I'm going to talk to you is the spontaneous time-reversal symmetry breaking in this twisted MoTe2 bilayer. Here's a schematic of a device where we have a twisted MoTe2, and in this dual gated structure, we have a top and a bottom gates. And these top and bottom gates can control the carrier densities and as a vertical electric field across sample individually. And we define this fitting number mu means a number of carriers per Moiré unit cells. Okay. So on the left-hand side, what I show you here is a magnetic circular dichroism, right, intensity plot at the zero magnetic field. So the magnetic circular dichroism you can consider as optical absorption difference between left and the right circular polarized light. So it's a measurement of a Hawk conductivity, but the optical frequencies. So it's a measurement of magnetism. Now you look at these MCD signal intensity plot, right? The vertical axis is the fitting number, and the horizontal axis here is the electric field. Now we can see that in the phase space of hole doping, and with some in the range of electric field, there's non-vanishing MCD signal. So this just tells you here's a phase space of ferromagnetic orders. And there's two features here. You can see a little, bump here, right? That's correspond to fraction filling 2/3, and the other is the integer filling -1. So we can confirm this really ferromagnetism, right? For example, I can park my measurement at these conditions. They can measure this MCD signal as function magnetic field sweeping forward and backwards. You can clearly see a pronounced hysteresis curve. Okay, so that just really shows we have ferromagnetism in existence. So when we have these results, I talked to Liang Fu actually back to when I visited MIT in 2022. Yeah. So we know there's a series of predictions, right, from him and also from the other group is the system can have a fractional translator. By the time when I have these temporal symmetry breaking, which is the first step, and we're very excited, but I don't know how to measure topological invariant. So Liang is really excited. He basically saying, okay, well, just find whatever physical quantity you have in existence and just measure as function magnetic field. See if there's dispersions. If there's dispersions, you get a topological state. So then I said, okay, I know what to do. So I go back, just tell my students, let's measure something. That's what I'm going to tell you how we measure the topological invariant. But before that, I'm going to show you some new results that, right, initially what I show you here, right, temporal symmetry breaking is the filling factor near -1. Now we can extend the measurements all the way to higher Moiré chain bands. Okay, so in this case, we have a filling factor -3. So again, right, these plot I show you here, just a magnetic circuit diaprism measurements, right, at a 2.7 degree twisted MoTe2, but a 0 magnetic field. Okay, so now I sort of rotate my plot. The horizontal axis here is the filling factor. So the vertical axis here is the electric field. So you can see that, well, at the near filling factor -1, looks similar, right? We have these ferromagnetic states. You see these choppy features because of magnetization actually is flipping. And also at the filling factor -3, which is the second Moiré chain band, you can also observe non-vanishing MCD signals, which you see actually there's a strong interactions give rise to these ferromagnetic order. We can confirm that by just measure MCD signal as function magnetic field, the different filling number, right? The top is 2/3 fillings, -1, -3, right? You can see pronounced hysteresis. So we do have very many order in this Moiré chain band. I can also take a difference of this MCD signal with magnetic field sweeping forward and backwards. Basically, you just take a difference of these curves. What you left over then is just a hysteretic component, right, in this measurement. So left plot is this hysteretic component as function filling factor. So clearly you can see that there's enhancement of cohesive field at the -2/3 fillings, the -1 fillings, and there's some features of -3, but it's not as strong. Okay. So the state itself is quite robust. So here what I show you is that this hysteretic component as function of a temperature, right? This middle panel shows that the mu -3, the Curie temperature is between 5 to 6 kelvins, and for filling factor -1, the Curie temperature between 9 to 10 kelvins for these around 2.7 degrees. So this just shows that we do have a very robust ferromagnetism for the first and also for the second Moiré chain band. So now I'm going to show you how we determine the topological invariant, right? I already mentioned to you what we did is we basically measure the density corresponding to this incompressible state as function magnetic field. So you map out this dispersion curve, then from strata formula, you can determine the chain numbers. So this is the technique you use when you cannot do transport measurements. So this example, right, the SET measurements determine its fractional translator. And also here I show you the example of STM measurements of the translator in the magic angle twisted graphene. All these just measure the dispersion curve of this incompressible state. So in our lab, we don't have SET, we don't have STM. So what we did is use optical technique. So we basically use the trions to measure these topological state. So just give you brief instructions, right? In case you don't know what the trion is. So if you have a semiconductor, and if you shine light to a semiconductor, you create an electron and hole pairs. So each electron and the whole pair, they bond together. So they form these exciton. In this case, it's a neutral one. And you can also dope the system. For example, I double host the system, then these neutral exciton can bind to extra carriers. Now we form a charged exciton, so we call it trion. So in this charged exciton, right, we can distinguish the neutral and the charge by just measure the luminescence spectra. In this case, the example is MoTe2. It's a monolayer, where you can see I have a little peak in my spectroscopy measurements. These correspond to the neutral excitons. And also I have trions. You can see exciton and the trion has a very different energies, right, in these horizontal axis. Their intensity also different. So we can measure these luminescence of these monolayer as function of a carrier dopings in these vertical axis. What I show you here is just intensity plot of the luminescence. Now you can see this little feature at the charge neutrality. It's my neutral exciton. And as I dope it, right, you can find there's a negatively charged trions, you have a positively charged trions. It will vary continuously as function of dopings in terms of energies and intensities. Now what I show you is the same measurements, but in the whole doping regime for a twisted bilayer MoTe2. Now you can see that actually at these fractional filling minus 2/3 and also at the integer filling minus 1, there's a little disruptive features, right? The intensity of trion is suppressed and also energy is shifted, okay? So those are the signature where formation of correlated insuline states. So a brief introduction of explanation of this is that right on the right-hand side, what I show you is a band diagram, right, for the twisted bilayer system, and I already use these Moiré mini bands for the valence band. So when the correlated insulin state formed, means the Fermi surface will be gapped out, right? So when we gap out the Fermi surface, then the number of free carriers should reduce. As I mentioned to you, a trion is a exciton bind to a free carriers. Because the number of free carriers is reduced, then the population of a trion is also reduced. Then direct consequence of this suppression of trion population is the suppression of its luminescence intensities, okay? So now the take-home message is that in such a system, when you see the trion luminescence is suppressed, you know that there's an incompressible state. So now we can just map out these incompressible states by measure trion luminescence intensity as function of a magnetic field. So here, the vertical axis magnetic field, horizontal is carrier densities. You see the three obvious features, right? The luminescence is suppressed. Okay, so you can also see the three states here. Actually, they have these dispersive features, right, as function magnetic field. So that's my Venn diagrams, but I use optical way to detect it. So with this Venn diagram, I can extract the position, the topological states, right, the density corresponding to these three incompressible states as function magnetic field. The bottom here, and all these lines actually is the expected dispersion curve from Strader formula, but without any free parameters in the systems. So now you can see that the measurement actually agree with these Strader formula analysis. So basically, at the chain number, at the filling -1, we have these quantum anomalous house state. And these two fractional filling, -2/3 and also -3/5, we have these gene sequence of a fractional changeless states. And the beauty of these states is that it extends all the way to zero magnetic field, because I already show you that, right? The zero magnetic field is there's a spontaneous Fermi orders. Okay? So this measurement here, it gives you a thermodynamic evidence. We have these fraction quantum anomalous effect, but it's not a direct measurement.
Can I ask a question?
We can do a bit of analysis of the data. What I show you here is just intensity, right? We can take a little bit of analysis. What we do is here, I take derivative of my intensity to the filling factors. So this just gives rise, better contrast of my data. You can see that in addition to these -2/3 and -3/5, actually there's extra feature of -4/7. So these all belong to the gene sequence of these fractional chain state. Okay, so now the second part, I'm gonna show you the transform measurements, which I think you consider as a more direct evidence of a fractional quantum anomalous effect compared to these strata formula analysis.
May I ask a question?
So, the bottom, right, just show you the optical microscope image of my sample. It's a 3.7 degrees twisted MoTe2 bilayers, and the sample is really clean, shown by these atomic force microscopy image. And these two panels here, right on the left, what I measure is the longitudinal resistance, which is Rxx, as function of carrier density in the vertical axis. Sorry, carrier density is the horizontal axis, and the vertical is electric field. And the right panel is just corresponding Hall resistance Rxy. And the data is already symmetry and anti-symmetrialized at 50 millitesla. So you can just consider it as 0 Tesla data. Now, the data shows many interesting features, right? And I want to walk you through some major features. The first one is that at the filling factor -1, right? You see there's a large phase space with deep blue. Deep blue means Rx actually vanishes, okay? But correspondingly, we have a very strong Xy. Actually, it's quantized in the edge of these squares. So this is my quantum anomalous Hall phase. Then there's another suppressed Rxx pocket, right, near the fraction filling -2/3, and we have a corresponding enhanced Rxy. This one is quantized in the units of 3/2. So this is my fractional chain insulated state. There's another phase space near -1/2 filling with suppressed Rxx and also with enhanced Rxy. That's I'm going to talk to you at the end, which is suspicious. Basically, we think it's a putative composite from a liquid phase. And between the phase -1 and the -2/3, right, you see another pocket of suppressed Rxx, but also Rxy is also suppressed. But it's not a vanishing; it's just suppressed. With the number is about a couple kiloohms. So these phase correspond to the ferromagnetic metal phase, or anomalous Hall metal phase, for example, as predicted by Landau and Valentin, for example. The another interesting feature is that if I go these vertical directions by increasing electric field, right, you will see that at the small electric field, Rxx vanish, right? But as I increase electric field over certain values, goes to this dark regime. Means dark means Rxx is too large to measure. So it's on the other few megaohm to tens of megaohms. So these from these vanishing Rxx to very large Rxx tell us that there's a topological phase transitions from this quantum anomalous Hall state to a modern insulating state. Okay. And similar feature can be analyzed at these fractional filling -2/3, for example, where you have a small Rxx to a larger Rxx and to a small Rxx again. So there's another electric field induced topological phase transitions. Yeah.
Depends here that one can interpret as gap versus gapless states, or is it all at very low temperature?
So we did a temperature dependence, and you can, the reason the temperature dependence here is you can, Rxx initially was small, right, close to 0. Then you can see the increase and to a certain values. So it gives you a activation behavior you can estimate the thermal activation gap of the systems. Yeah. But it's not so if you want to measure insulator, for these guys, right, then you can do different temperature. It's the same temperature dependent measurements, but they give you different physics. One is a thermal activation gap of these chains later. The other is the gap for topological trivial. So I'm going to show you one example. Yeah. Okay. So
sorry,
yeah.
There's a question online. Is there a way to unmute Antoine?
Can you hear me or not?
Yeah, 1 second. Thank you so much.
Go ahead, Antoine. Oh, okay, thank you. Hi. Yeah, I was trying to ask this question for a while, so it actually refers to previous slides. But in several instances, you show the result of the Streda formula, right? And I would like the straight lines here. I want to understand a little bit better how this is done experimentally? Because to do that, you need to measure at constant chemical potential. So what do? You fix the gate voltage and measure the change in carrier density. How is the NDB at constant mu measured?
Yeah, so what we did here is that I don't think we measure chemical potential per se. So what we measure here is determining the dip positions of these minimum PO intensities. So that's my carrier density corresponding to a particular state. Then what we measure is these intensity as function of a magnetic field. Okay, so from there we determine these carrier densities corresponding to this particular state, and that's function magnetic field. That's what we get. Yeah, I don't claim we measure chemical potential. Yeah,
I see. So whatever you do, it sort of works, but you can't guarantee that the mu was kept fixed.
So what we did is the density is fixed. And then what I try to infer here is that whenever there's a dip position in my PO intensity, right, the dip is corresponding to the gap to, the incompressible state. But what I cannot claim is I don't directly measure chemical potential.
So if you fix n, you're not directly measuring the NDB, which is what the formula is telling us to do, right?
Yeah. So what I'm trying to say here is we measure these dispersion curve of the states, so we can analyze these Venn diagram, use the strata formulas. At least it matches the strata formulas.
Okay.
Yeah. But I cannot determine from measurement to say where the chemical potential is. But in principle, of course, right? If everything matches, it in essence, it is tell you something about the chemical potential. Otherwise, you cannot do this. Yeah. That make sense? Yeah. So now what I show you here is that we measure these Rxx and Rxy as function of a magnetic field. Okay. And first at the filling factor -1. Now you can see Rxy is quantized at the zero magnetic field, right, in a unit of Hg square, and with Rxx is suppressed. So that's just the quantum anomalous effect as I talked to you, when as a trade rule they observed. And we can measure these at a few different trace angles. The example I show you here is 3 from 3.5, 3.7 to 3.9. And they all look similar, right? You have a quantized Rxy, the zero magnetic field, with suppressed Rxx. So this just shows that this quantized anomalous effect is actually quite repeatable and insensitive to the trace angles. So basically, you can see this from right now we have sample from about a 2.7 degree all the way to 3.9 degrees. Okay, so it's quite robust against these trace angles. Then the effect itself also is high temperature. Right here, I show you the temperature dependence from 1 Kelvin to 4 Kelvin, 8 Kelvin, 10 Kelvins. You can see that even at 10 Kelvin, Rxy is nearly quantized. So to emphasize this head temperature effect, where I refer you to this beautiful piece of article from Yoshi Takura to celebrate 10 years anniversary of this quantum anomalous effect. So the end, right, what Yoshi pointed out is that the challenge is to push this quantum anomalous effect to higher temperature, right? The first to 4 Kelvins, then to room temperatures. So I think twist MoTe2 is actually quite promising because, well, at the 4 Kelvin, you can see it's very much quantized. Okay, so I think it's a promising system to realize this high temperature quantum anomalous effect. And the effect itself is can be electro-tuned. What I show you here, the blue is Rxy and the red is Rxx. We measure them as function of electric field, right? Continuously tuned. So you can clearly see that above this critical electric field, around 150 millivolt per nanometer, you see these Rxx quickly rise, right? Where Rxy drops. So these already tell us that we have a transition from these quantum anomalous state to a topological insulin state. And we identify this insulin state is actually it's ferromagnetic. So we can also do temperature-dependent measurements, then infer the thermal activation gap of the systems. So what I show you here for this is a thermal activation gap, right? It's around 30 to 40 kelvins at a zero electric field. And as the electric field is large, close to a phase transition, you can see the gap is quickly reduced and closed, then reopens again. So these close and reopen the gap, basically it's a hallmark of a topological phase transitions. And at least our measurement shows this is a continuous phase transitions. Now we're going to shift gear to these fractional state. Yeah.
Question going back to that. How do I know? It should be. The little green light is on. How do I know that this is really a continuous phase transition rather than being a consequence of phase mixture around a first order transition?
Yeah, so what we did a few things, okay? One thing I didn't show you is that we measure these RxX or RxY continuously as a tuned electric field back and forth. We don't see any hysteresis. The second is what I show you here, where we see the gap is actually very much closed. And I'm going to show you the third example a few minutes later. So from this evidence, at least from what we know, is looks like a continuous phase transitions. Yeah.
Okay, this is working. So just to understand, the two phases have the same ferromagnetic ordering. So can be this transition can be understood by just a band inversion.
That's correct.
Okay.
The gap is closed. Yeah. Yeah.
If there is a singularity in thermodynamics, that presumably means that the ferromagnetic order parameter has a high order non-electricity. It's
high order for
non-electricity. Basically, if you were to carefully measure the ferromagnetic order parameter, there is some kind of, as a function of the electric field, there's some kind of a singularity there still.
Singularity of? As
a function of the electric field. In other words, it's constant on both parts, but there's a singular part.
I don't know how to understand the singularity.
Oh, some square root, you know. Okay, I can.
Yeah, I don't understand what you mean by singularity here.
Okay.
Yeah. But this one to confirm is that the whole phase I show you here is ferromagnetic. Until larger electric field, then the ferromagnetic phase will be killed. Yeah. But even that, our understanding is a still continuous phase transition for our measurement. Yeah. Okay, so let's go these fractional phase quickly, right? These the fraction filling in -2/3, right? We can measure these RxY as function of magnetic field, and also you can see these quantized at the 3/2 of h(v square, and we suppress RxX. So let's just confirm, right? We have these fractional translator and the -2/3 fillings. And again, we can do same measurements of at the -3/5 filling and get same phenomena, where you see these nearly quantized values, we suppress RxX. So we have these two fractional translator state. Again, right, for these -2/3 filling state, we can also use electric field to tune it, right? So the blue is the RxY, and red is RxX. You can see as the electric field is larger than about 20 to 30 millivolt per nanometer. So RxY will be small, and RxX rise first, and it drops again. So this tells us there's several phases involved, right? From this fractional translator to some kind of a correlated state and to some metallic state. Okay. The FCS state itself is also head temperature. Now I show you the temperature dependence, right? The top is 100 millikelvin, the bottom is 3 kelvins. Even at the 2 Kelvin, right, you see RxY is still nearly quantized. So the system is really a head temperature effect at a zero magnetic field. And what I show you here is a transport measurements. So basically in the transport measurements, right, it's still a global measurements. And from these observation of a quantized RxY with nearly vanishing RxX, we can basically conclude we have this quantum anomalous Hall and also fractional quantum anomalous Hall effect. But there's still complications, right? You know, some will argue with me, well, how do you know what's domain effects? How do you know these fraction value is not a mixture of something? So the key is that you still want to see, has some measurements shows that you have an insulin bulk and with edge conductions in these changeless states. You want the direct measurements, spatial mapping. So that's what we did in collaboration with ZAction and the postdoc Julie and Mark. They perform the measurements, and my student June Park, right, design and fabricate the samples. So what the ZX has is they have these microwave impedance microscopy system, and it can couple to the light. So here's the samples. So what this tip does is that you can do local probe of the conductivity of the samples. Okay. On the right-hand side, I show you the mean signal as function of electric field in the vertical axis. Horizontal is the doping. And the color scheme here is dark color means it's an insulating state, and the bright color means it's a conductive state, it's conductor. Okay. Now you can see in this phase diagram, right, at the filling factor -1, at the small electric field, there's insulating state. Large electric field, there's another insulating state. So this measurement is in the bulk. Okay. Then in the middle, the transition between insulator to insulator, actually there's a conductive metallic state, right? And again, you can see several other features, -2/3 fillings, -3/5 fillings. So again, I want to emphasize, right, the measurement itself is in a bulk. It's a bulk state measurement. You can take line cuts near zero electric field. You will see there's a suppression of local conductivity at the filling factor -1, -2/3, -3/5, and -4/7. Right? Very much like what we did in the optical measurements, which I also consider as a local measurements, but not as local as these scanning probe. You can see they show similar features. So now I can compare the mean measurements with my transport measurements. So in the transport measurements, right, again, right, it's a global measurement. Whenever there's a changeless state, we should see a nearly quantized RxY with a nearly suppressed RxX. But these mean measurements are local measurements, right? What the translator, right, is it's insulating in a bulk, but conducting at the edge. So this is exactly what these two maps shows, right? When it's in conduction, this edge measurement shows RxX is nearly vanishing at a -1, -2/3 filling, etc. But in the local mean measurements, the bulk should be insulating, right? That's what they see. You see insulating state of -1, insulating state of -2/3, and insulating state of -3/5. And they also see the phase transition from one insulating to another insulating connected by this metallic state, which gap should be closed. So that's all the measurements shows here is very consistent. One is local conductivity measurements, the other is global transport measurements, but the message is the same. Okay. More than that, what the ZX and his student, postdoc can do is they image the edge conduction channels. So they're starting with these filling at the -1.33, which is metallic phase, right? You see the whole image lights up. But you start to tune the density all the way to near these quantum anomalous state at the -1 fillings. Now you can see the bulk become insulating as the edge conduction channel appears. So that's exactly what you expect, right? For quantum anomalous, it should be insulating the bulk and with edge conductions. That's exactly what we observe. And you can see similar physics at the -2/3 fillings. You see there's insulating in the bulk and with edge conductions, and similar at the -3/5 filling. It's not corrected actually. Yeah, these should be 3/5 fillings, also with edge conductions and with insulating in the bulk.
Maybe what is the size of the?
Yeah, it's a few microns. Yeah.
Okay.
Yeah,
and is this black domain that?
Yeah, it's a few microns. So, yeah, it's not a small.
So how is the edge defined? Because it seems like there's a line and then there's another empty area.
Yeah, so here's a sample. So that's the edge. And the dashed line here is define my gate. So there's a little crack in the gate. So you can think of this as a physical edge of sample. This is a gate defined edge. So we have two types of edges. So both give you a similar phenomenon. Yeah. And the other thing is the system I just showed you, right? As you ask, actually we have two different domains because they're two different gate part. So what's interesting is that if you look at these line cuts of local conductivities, in one domain, you can have a -2/3 fillings, but the other domain can align with these actual -3/5 fillings. So this just shows you potentially in a system, you can have a mixture of fractional chains of the domains. So that's actually an interesting future direction to go, to really local control these FCI states and then form these domain structures.
Be homogeneous, the filling all over the sample. So why you want to form regions with different filling factors?
Then you can study the edge states, right? The mixing of the different FCI states.
Yeah, but why the filling is inhomogeneous across the sample?
Yeah, there's two different gates. Basically, the gate efficiency is different in this particular sample.
Okay.
Yeah. So that's why the trying to say is we want to do a local, really controllable, two different gates, individual controls. Yeah. But this sample what it shows is you have potential to do that. Indeed, you can have a, this is what people talk about. The mix, you can study the edge states between different FCI states if you can do a good job. Yeah. All right. Lastly, I want to show you these the feature nearest -1/2 filling. So what I show you here, blue curve is Rxy and the red is Rxx as function of this filling factor. Now you can see these Rxy, right, with enhanced, the 2/3 filling, another near plateau feature at the 3/5 fillings. Then the Rxy will linearly increase and across these two edges of the square at the half view of light chain band. So we can measure these Rxy at these half view of light chain band as function of magnetic field. You will see these Rxy actually is really large, right? At the value of a 2 edge of the square. But from these measurements as a function of filling factor, you know that the state itself is not quantized. It's actually compressible states. So we can try to understand the observation by comparing to what's known in the 2D electron gas, right? In these measurements, at the 25 Tesla, it's near minus, basically it's a half year lowest Landau levels. And they also observe these 2 edge of the square at the half year lowest Landau levels. And then now we know that the state is actually, it's a composite from a liquid state. Okay? I'm not going into details. It's being proved by many groups. So if I compare these 2D electron gas system to what the twisted MoTe bilayer, right? In these 2D electron gas, you will see there's a plateau corresponding to 2/3 fillings, another plateau, 3/5 fillings, and a couple more. Then these Rxy will linearly increase as function of a filling factor, in this case, right, tuned by magnetic field, and across these 2 edges of these squares. So it's very similar to what we observe here. The difference is that we don't tune magnetic field. What we tune is really the filling factor of my Moiré chain band. So we have a 2/3 filling, we have 3/5 filling, then some wiggles, then linearly increase across 2 edges squares. So phenomenologically, what I have here, right, at the half-year flat chain band, is resemble the observation in the half-year lowest Landau levels. So it looks like it's a composite from a liquid state, but there's zero magnetic field. And if only, I don't think we have a definite proof. What I have is phenomenologically these two look similar. But from a theoretical point of view, right, pointed out by Liang Fu and his collaborator, and also Ashwin, Daniel Parker, and their collaborator, is that in half-field flat chain band, right, in this twisted MoTe2, indeed, right, it's a zero field and composite from a liquid state from a theoretical point of view. But I think there's a lot more experiments to be done to confirm this is correct. Okay, so here's my summary. I think this is really exciting, right? The 1980s, right? Von Clinton, right? We discovered these quantum Hall effect in the silicon transistors, and a couple of years later, in gallium arsenide systems, and the group, right, Daniel Tree, Stormer, etc., they discovered these fractional quantum Hall effect. And about 30 years later, from all these, right, at 2013, now we have these quantum anomalous Hall effect, which is a quantum Hall effect at zero magnetic field. And last year, right, finally, we observed these fractional quantum anomalous Hall effect. Okay, so really complete these Hall families. So I think it's an exciting time. But if I compare to the state of the art, for example, here is the measurement of gallium arsenide, right, from these Roland Favre and the collaborators, right. This probably is one of the most beautiful curve in the condensed matter. You will see there's so many beautiful Gibbs, right? Basically, tons of fractional quantum half states. And this is the figure we have now. But we have a bunch of states, but none of them look like as beautiful as the gallium arsenide. Right? Because gallium arsenide has a 40 years history of development of the materials. So I would say our materials is not as good. The device probably is still lousy, but I feel like, well, I don't think it is a negative thing. It means there's a lot of room for improve. So even though we have not there yet, but I think is a fraction quantum Hall anomalous Hall effect. Actually, it's a really beautiful platform to search for new quantum states and possible new physics, right? I already showed you today, right? We have a trace angle. We can control them by doping a large field pretty easily, right? See all of the phase transition, which seems very easy to do, but actually, I think it's hard to realize in any other systems, right? But in this system, it's so easy to realize because we have controls. And from the 2D material research, we know we can also control a system with strings, with pressures, etc. And I show you today, we can also use light, right, to excite these excited state at the 1 eV scales, but still know what's happening in the mini eV, these many body states. So there's another opportunity. We can use these optically excited state to probe these many body ground state. And another opportunity I really like is the photo emission spectroscopies. Because we know photo emission spectroscopy doesn't like a magnetic field. They cannot go down very low temperatures. So you cannot use photo emission to measure these, for example, fractionally quantized state. But because our system can go above 1 Kelvin, doesn't require magnetic field, now provides opportunity to use photo emission spectroscopy to measure these many body states. Okay. So I think there's a lot more opportunities coming. Okay. So with that, I will thank my collaborators, right? I have theory collaborations with Wang Yao, Di Xiao, Ting Chao, Ran Ying, recent collaboration with Andre, with Nikolai. And in transport measurements, I have a collaboration with my colleague, David Copton, Jinghao Chu, and also Chizhu Chang at the Penn State. The mean measurement I show you, right, from ZX and his postdocs. And we have a boron nitride crystals from these 2 famous Japanese scientists. The end, I'd like to thank my 3 heroes. Those are the 3 students actually really carry out all the work I talked to you today, and with support from the whole groups. And I thank the funding agencies, and thank you for your attention.
Thank you so much for coming and sharing these exciting results. More questions for Xiaodong? And also for people online, if you type in your questions or just indicate so we can unmute you.
Andy.
Andy, go ahead.
Oh, all right. So also important and interesting in the fractional quantum Hall state was spectroscopies like Raman scattering that Aaron Pinsuk did, for example. So is there a prospect of doing that either directly or indirectly via Trion sensing to see what the collective modes are and how they might differ from the quantum Hall ones?
That's interesting questions. We haven't tried it, but I think it's an interesting direction to go. And also I'm actually collaborating with Xiaodong to match these. He has my samples, try to match these collective modes, use time resolved techniques. Yeah. So that's what we're doing, yeah.
So you show us several samples, and you mentioned that for the quantum anomalous Hall state, at filling -1, the twist angle is not so important. So I was wondering whether for other filling factors, being at a certain twist angle is important in order to observe the state. So for instance, at a certain point, you mentioned that you also see anomalous Hall fissure at filling -3.
Yeah.
So is that
so for this -3, for example, you can see it all the way from what I have now. The sample is about 2.6, 2.5 degree, all the way to about 3.9 to 4 degrees. So it's all there, very robust. So the FCS states is also robust in this region. Like -2/3 states is very robust. -3/5 is it's a bit trickier because the gap is smaller. So sometimes at a small twist angle, we haven't see, I think we see signature, but it's not as clear as this 3.7 degree. So I don't know because of a twist angle or just my measurement. Because when you're a theorist, right? Let me give you some idea why it's hard. So when you go the small twist angle, right? If you think about the carrier density is 1 divided by carrier per Moiré unit cell, right? Divided by the area. So when you have a small twist angle, the Moiré cell gets larger. So the carrier density corresponding to the particular filling factor actually gets lower. Make sense? So now when you go to -3/5 fillings, then the carrier density of a 2 point, for example, say 5 degrees, right, which is much smaller than 3.5. So the electrical contacts actually stop working at low densities.
Okay.
So the measurement itself is suggesting has 3/5 from our data, but it's just not clear enough because of the contact doesn't work as good as at these high twist angle samples.
So you would say that there is no magic angle in this.
I don't think there's a magic angle.
There is a, okay.
No, at least from what I have now, all the feature we observe is there over 1 degree twist angles. But there could be magic angle for how flat the band is. Maybe there's the magic angle, there's magic feature can appear, which we haven't achieved. So the correct statement is, I don't know if that's magic angle.
Yeah, I'm not familiar with the system, so just a basic question. So the ferromagnetic order, does that have a very high transition temperature? And so that's mostly sort of frozen by the time you get to these low temperatures. Does that depend on the twist angle, or is that?
So anomalous Hall signal actually can survive all the way to Curie temperatures. So basically the anomalous Hall signal itself almost like a vanishing when these ferromagnetism vanishing. So
but what's that temperature?
Oh, 10 Kelvin above. And of course, it's filling factor dependent, right?
But the physics of ferromagnetic ordering is independent of theta or of the twist angle. Is that sort of inherited from, or does it depend also on?
They basically, I think they are kind of tangled together. Yeah,
I see.
Tied together. Yeah, they're not separated.
Yeah. So the other question is that I never heard of tryons in the context of conventional gallium arsenide based quantum Hall effect.
There's a tryon actually. We're not the first one doing it. Yeah.
Is there a fractional tryon where you bind?
That's a very good question. So there's a paper from a Japanese group or some groups, right? They claim, okay, so that's what they do. They measure tryons in a fractional quantum Hall state. So there's a fractional quantum Hall state, right? Then they see a tryon. So they claim this is a composite of tryons. But I don't think it's a direct measurement. Because in my case, I also see FC, I also see tryons, right? I don't think my tryon is a composite tryons. You know what I'm saying?
Yeah, I would be interested to know how to distinguish.
I don't know. I don't know whether my tryon is bind to, for example, fractional charge. For example, right? Say 2/3 filling, right? You have a 2/3 charge. But I don't know if my tryon is bind to this 2/3 charge or not. I have no idea. Yeah. I think so. I think the binding energy will be different. That means I have to find a way to determine the binding energy of these tryon bind to a fraction charge and the tryon bind to a charge. I don't know the theory part. I know the experimental observations is what they basically observe the tryon features associated with these fraction quantum states. And the claim is that, at least if my memory is correct, is they claim there's a tryon, like a composite fermion type feature. But
okay, let's carry on the discussion.
But I'm just not sure if it's direct proof or not. Yeah.
So let's thank Xiaodong again.